Let's start. What did we do last time? If at every point R, the three unit tangents are orthogonal to one another, that is, if the dot product follows the Kronecker delta. Um, yeah, or if the dot product, the difference between this and this is just multiplying by the h, which is the length of the partial in a certain direction. Then the generalized coordinates UI is said to be the form orthogonal OCC. The system unit tangents form Cartesian coordinate at every point R. The only complication is that the orientations change from point to point in space. Yeah, we saw that. Metric coefficients, this are diagonal, which means if you represent them if you represent them in a matrix, only the diagonals will have values. Everything else will be zero. Um, and the square length ds squared equal this. Yeah, it doesn't, and the square length does not contain cross terms. Yeah, the quantity dsi always has the dimension of length. The differential elements of surface and volume become this dsi dsj sum of, yeah, d tau equal ds1, ds2, ds3. Thus the dsi are very much like rectangular. Wait, draw. Okay. However, the tangent, shoot. However, the tangent directions ei of r do change from point to point. Okay. Except in the special case of rectangular coordinates for which you are concerned, your vectors. For spherical, direct calculations with tangent vectors show that, yeah, they are all orthogonal. And also these orthogonality proportions are easily visualized because ER points radially. Yeah. E theta, yeah. Also with DSR equal DR, DS, what's DS? DS is just the length. Um, well, let's go back a little bit. So DR, so the differential of the position vector, you can break that up into the partials of UI, the three different UIs, the three different like uh, coordinates, three different axes you can break that off into. And um, the direction should be in the direction of the axis we're differentiating into, and hi represents the length. Uh, okay, ds equal dr, ds theta equal r d theta. Here we find ds squared, yeah. Is anyone here? Docs, chat, connecting chat. I don't think anyone is there. So I can relax. I can relax. ds squared equal dr squared plus rd theta squared plus um yeah, we started from here. ds squared is just the hi squared, right? Yeah. The theta r theta will point in the phi direction. Yeah. We can also define coordinate surfaces on which one of the coordinate is constant while the remaining two coordinates change. The coordinate surfaces for spherical coordinates are spherical surfaces of constant r, conical surfaces of constant pi. Now, theta and half planes of constant phi for OCC systems, coordinate surfaces are perpendicular. A perpendicular coordinate surfaces are perpendicular to coordinate curves along which the third coordinate changes value. For example, spherical surfaces of constant r are perpendicular to coordinate curve ER. Okay, we're almost done with the recap. We also did one UI, definition of UI, and scale factors in 2 common OCC. Okay, scale factors is the word for H. Okay. Um, Finally, we should know that the coordinate r of t of a physical event is a function of time. This can be differentiated with respect to time to give velocity acceleration. If curvilinear coordinates are used, there will be contributions. There will be contributions from the time variations. If curvilinear coordinates are used, there will be contributions from the time variations of both the tangent vectors and the curvilinear coordinates themselves. More specifically, we find by doing some stuff that, yeah, well, we found this out the hard way. Yeah, um, well, let me zoom out a bit. Velocity equal the change in the position vector over time, yeah, which is, okay, this is one direction here, but when you sum it up, you'll end up with 3 directions. So, yeah, it doesn't point in one particular direction, it points in a combination of all. Uh, A equal B dt, so you have this, after you differentiate it, you get the normal EI, but what is E dot I? Okay, you have a number, and then you have um, unit vector, and then you add, this is another number here, and this is dE dt. Did this change anything? D dt E. There will be contributions from the time variations of both the tangent vectors and collinear coordinates themselves. Tangent vectors. We'll move on. Velocity in spherical coordinates. For example, v equal. Okay, well, let me erase because I can't really see through this. So we're just applying this to spherical coordinates. So this is the first term. EI is ER. HI is HI is 1, I think. and then UI dot. UI is R. Okay, R dot. Yeah, the dot just means DDT, like differentiate with respect to time. Then do this for this, we do this for this. Yeah, it makes sense so far. Um, since it is also true that V equal DDT R equal this, we can see that the ERDT. Okay, so when you differentiate a guy, a unit vector with respect to time, it may also like change the direction of it, because now it's pointing in the theta and phi direction. Hmm. Hmm. Okay. A result that can also be seen by direct differentiation of ER and Bling. Similarly, we can find a direct differentiation of d theta. Okay. These are the basic relations that can be used to simplify the time rate of change of any vector. These are the basic relations that can be used to simplify the time rate of change of any vector field expressed in terms of spherical coordinates. Okay, so you have a vector field. It's expressed in spherical coordinates. Um, Time rate of change. Hmm. Time rate of change of a vector field. Okay, well, let me try and draw it in my head. So this is the radius of a circle. And when we say over time, it goes from here to here. How does the vectors look like? So R remains constant. Um, I think this hmm, circle, bigger circle, arrow, 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 circle, circle, circle. I mean arrow, arrow. Hmm. DDT. Hmm. Let's continue. Let's continue. Oh, this is the end. This is the end. Okay, let's go on XYZ for different coordinate systems. Ah, vector differential operators. What's the time? 14 minutes. Vector differential operators in orthogonal curvilinear coordinate systems. Vector differential operators. Since the generalized coordinates are equal to u1, u2, u3, define a point in space. Point in space. I'd rather use red. Define a point in space. Scalar and vector fields in space can be written as data chi. I don't know. Um, can be written as ding u1, u2, u3, or v u1, u2, u3. In performing vector differential operations on such fields, it is of course possible to change variables back to rectangular coordinates before applying the vector differential operator. It is possible for us to change this back to rectangular before applying the stuff in the normal rectangular form. This procedure is often unwise because the calculation may become rather complicated and the insights to the problem that might have motivated the use of a special system of coordinates might be lost. The purpose of this section is to show how such calculations can be made directly directly by using the generalized coordinates themselves. The procedures are not very complicated and are well worth mastering because they give insight to understanding of generalized coordinates. We will restrict ourselves to OCCs. That implies there are other systems. Let us start with the gradient function of a scalar field. At every point r, it describes a vector that can be decomposed into components. Okay, we have this. At every point r, it describes a vector that can be decomposed into components along the local unit tangents. EI. Bling, bling, bling. Okay, no problems yet. Summation of tree. Okay, they just split it up into the unit vector and like the magnitude, I guess. Okay, the I component multiplied by the I direction, j component, j direction. Where the I component is like, I forget what they call this. When you dot product into a unit vector to get projection, it's kind of like projection. It's projecting onto the um the axis of the EIR. Yeah, anyways, when you do this, you get so this is just this del phi. Yeah, nothing crazy yet, is there? Why are we in X's? EIR. The direction, yeah, direction cosines is what I was thinking of. The direction cosines involved turned out to be just the partial derivatives. Ex dot ei equal ex dot ex dot ei equal ex dot del r del si del r del si. What is s? S is HRI dui. Hmm. Okay, well, let's continue. Ex dot del of xex plus yey plus zz. Yeah, and we don't care about these guys because with dot producting, and there's there's zero EYs and EZs over here. So it'll just be 0 times this plus 0 times this. We end up with, oh yeah, and dot product, um, the result isn't a vector anymore, it's just a number magnitude. So this is actually just 1 multiplied by del x del si. Hmm. Del si ei ex del phi del x. Uh, Hence the ith component of this guy up here equal del phi del x, del phi del y, del phi del c. You basically brought this guy inside, and ei dot ex we found to be this, so just join them up. Okay, and you can combine all of these to just mean del theta, del. I forget the symbol, del phi, del chi, del scalar field, del si. Let me just Google it real quick. It shouldn't be that hard. Greek letters, Greek alphabet, Greek alphabet. Alpha, beta, gamma, delta, epsilon, zeta, eta, theta, iota, kappa, lambda, mu, nu, xi, omicron, pi, rho. Sigma, tau, is phi, is phi. Um, let me just bring this guy here. That is really big. Uh, I regret doing this. Z, okay. Um, okay. We found this is this, and so the ith component of this is this. So all the way over here, we can bring this all the way down here. This side is unchanged. The sum of EIR, d theta, d phi, del phi, del si. That is UI. That is the UI in this can be treated as if they were rectangular coordinates. If the local lengths EIR are used together with the dimensional displacements dsi equal hi dui. Uh, that is UI in this can be treated as if there were rectangular coordinates if the local tangents are used together with the dimensional displacements. Hmm. Why are we relating it to rectangular coordinates again? In rectangular coordinates, the gradient of phi is what? Del phi, del x, del phi, del y, del phi, del c, del x. Si is usually x. Um, okay, it makes sense. It makes sense. Si is usually x. So if we If these were not differentials, right? If these were just normal guys, they're not small pieces. X equal HI X. Well, SI equal HI X. But HI is just the the length of the differential. The length of the differential, the partial differential. But in like Cartesian, that length is 1. So it'll be SI equal 1x, which is what we expect. Woohoo, woohoo. So yeah, it makes sense. Yeah. Um, Calculate gradient of r squared sine theta. Okay, so we're treating this as if it was a scalar field, I assume. Is that a thing we can do? Yeah, but oh, it's just spherical coordinates now because the r and the theta. Maybe they should specify spherical coordinates. Maybe this is enough information to be like, oh, spherical coordinates. Um, According to blah, r squared sine theta, the gradient of phi equal gradient of phi. We're saying this is the gradient. Y del del r er. Yeah, yeah. Okay. Hmm. Gradient phi. Gradient phi. Whenever we see gradient, we can just imagine this thing here. The EI and the del SI. So this is EI here. This is del SI. EI del SI. EI del SI. Yeah. Hence, gradient of this equal, okay. Um, this, why did this disappear? Del R. Okay, okay. I think I see where it's going. This thing here is actually r squared sine theta. The partial difference, the partial of this is 2r sine theta. Yeah. So yeah, good. Um, hmm. Del theta. Del theta. Okay, interesting that this is considered a constant. So 1 over r, and this this differentiated by theta is sine tangent cos r squared cos theta, but divided by r, get r cos theta, yeah. And this differentiated by phi, there's no phi here, so this is actually just like a number. And when you differentiate a number, it's 0. So yeah, the gradient of the scalar field r squared sine theta is this. 2r sine theta in the er direction plus r cos theta e theta direction, and 0 and 0, phi. Nothing in the phi direction. So nothing ever goes in the phi direction. So maybe it's like a plane or something, I don't know. Maybe. Okay, perhaps the most interesting gradients in the curvilinear coordinate system are those constructed from the curvilinear coordinates UJR themselves. UJR. I don't know why we're using J now. Okay. Most interesting gradients are those constructed by the coordinates themselves. So gradients of the coordinate equal EIR. Oh my God. Equal EIR. So the direction, that is the magnitude. Well, what did I say? Del equal EI del SI. Okay, I think this is useful enough that I should screenshot it. Yeah. Okay. Go over here, paste. Um. You. Um. Transform. Go over here. Go over here. Go over here. Make a little bigger. Boom, shakalaka. Okay. And deselect. Okay. So wherever you see del, you can replace it with EI of R del SI. Okay. Um. Well, the sum of this, so three of this really. The three of this for the three different coordinates. So EI, yeah, we see that, yeah. The UJ goes on top because that's the thing we're finding the gradient of. And del SI is HI del UI, yeah. Del SI equal HI, yeah. Okay, everything adds up so far. HI, so when you sum all this up, we're calling it EJR and HJR. There's no dells and stuff in there. EJR. We already went through all the EIRs. EI, UJ. Are those constructed? EJR. We started off with UJR. Well, let me just read. This result expresses the fact that the gradient of a coordinate changes most rapidly along the coordinate curve. It also shows that EJ is normal to the coordinate. It also shows that EJ is normal to the coordinate surface defined by the equation UJ equal constant. I agree with this. The gradient changes most rapidly along the coordinate curve, yeah. It also shows that EJ. What I'm trying to figure out is the difference between UJ and EJ. Although it's constructed from the curvilinear coordinates UJR. Curvilinear coordinates UJR. UJ. It also shows that EJ, unit vector in J direction, is normal to the coordinate surface. Normal to the coordinate surface defined by the equation UJR equal constant. I know what they mean. I know what they mean. I'm just trying to figure out what EJ and UJR is. Let's keep reading. Now the gradient of a scalar field is always irrotational. Hence, gradient of a scalar field. This is a curl. Yeah, that's just the definition of irrotational. Gradient of a scalar field. Hmm. Gradient of a scalar field is always rotational, so hence this. Okay. Since um since the curl of this, oh my god, spooky -1. Since the curl of this equal so we're splitting it into two terms. Uh, since this equal this, we find that generalized coordinate curve has a natural curliness. Okay, let's try to make sense of this. This cross a fraction. So what I'm thinking is they brought this to the numerator by like putting it to -1, like how m over s is ms -1. So maybe they're just doing that. EJ, HJ -1. Okay. So apparently when you have the curl of a product, it's some kind of weird product rule where it splits into two curls. One, hmm, hmm. The gradient acts on HIJ, and then that is crossed into EJ. Okay, during all of this, nothing really happens with the cross. You still need to cross afterwards. Okay, this goes into this, so you get del H I -1J. And then we're left behind with EJ dot EJ, well, with the arrow. Now this goes into this. So, this goes into this. Hmm. Maybe it's something like there's a 1 here, there's a 1, and this is like a product rule. Maybe, maybe. EJ. Let me do that over here. 1 EJH. U cross. You touch this. This cross this is 1. Well, just this guy again, right? And you still have this guy to deal with, and H has no business there. He can come out. He doesn't want to be here anymore. Now we touch the H, so it's a gradient H. J minus 1. The cross E is still there, and the 1 comes outside. Does that make sense? It 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 makes it look like this. We will go with that for now. We've now the gradient is also rotational, hence this is this equals 0. Wait, this equals 0. So this entire thing equals 0. What are we doing? We find that a generalized coordinate curve has a natural. Are we not going to address this? This is 0. Does this equal this? We find that the coordinate curve has a natural curliness of the curl of EJ equal. Okay, I see, I guess. We want to get the HJ out of here. So we're just multiplying both sides by HJ. So now it's over here. The HJ cancels out with this HJ here to just remain with this. And the HJ comes here now. Um, hmm. Although the so we have Nabla cross EJ. And now we have over here HIJ H minus HJ minus 2, no. HJ minus 1 gradient HJ minus 1 cross E plus this cross E. HJ, there's a minus over here for some reason. HJ minus 1 EJ. So these two terms line up perfectly, but there's a minus here. And we have this guy here as well. Why is this the case? This cross this equals 0. Maybe we're allowed to set this as 0, but then how this is negative? One consequence of this is that the color vector VR equal the sum of EJ, VJR, yeah, has contributions from both EJ and VJ. What even is going on? What even is going on? Let us start with gradient of this equal this at every point. Yeah. Yeah. That is, yeah, all this made sense. I'll drink some water, then I'll try to see what is going on here again. Let me update the confusion meter, I guess. Confusion meter goes ah confusion meter. Oh my god. Confusion meter goes to yellow. Okay. Um, Perhaps the most interesting, different color, different color. New me, new day, new me. Perhaps the most interesting gradients in a curvilinear coordinate system are those constructed from curvilinear coordinates UIR, UI of R, right? So R, theta, phi, and all of these functions of R, yeah, I think that makes sense, yeah. The gradient of one of these guys equal the sum of um well earlier up here we saw that you can replace the gradient with EIR del del SI, yeah. So gradient of this is just this. I agree. This part here now. I think this is the root of my confusion. This result expresses the fact. I don't think they're going to explain this, so I need to look into this more. UJ EIR gradient is EI del SI. Hmm. Maybe the confusion stems all the way here where we're using X's and Y's and Z's. Let us sum of this every point that can be decomposed tangents. This result expresses the fact that the gradient of one of these guys changes most rapidly along yeah. It also shows that EJ is normal to the coordinate surface defined by the equation UJR constant. So radius being constant, we just have a normal shell. We just have a shell. It shows that EJ is normal to the constant surface. So this is the constant surface. Over here, the normal points in the ER direction, ER. Um, EJ is ER. EJ is ER. Denoted by the equation UJR equal constant. UJR is constant. UJR is constant, and I think that is also R. R of R. Radius, which is a function of the position. So R of R, the gradient of R equals the sum of the EIs. The EIs, del SI, del UJ, del R, yeah. EJ. I think what this is getting at is at the end of the day, when you sum up all these I's with all the I's here, it will end up pointing back in the direction of UJ, which is EJ. Um, so yeah. Now what about HJ? What is HJ? Del UJ del. Another confusion is where did all the del's go? Did we really differentiate? Is that a thing we did? Del UJ del UI. Okay. Let's compute this. So EI would be ER 1/1 del R of R. Wait, no, don't wait, don't wait. Del UI. Del UI is what now? Del UI. Just del R. Okay. Del R. So this should just be 1. This is wet already. E theta should be 1/R, I think. Yeah, 1/R. Del R R del theta R. We don't need to write these R's all the time. I don't know why I'm writing them. Del R del theta. Del R del theta. E phi should be, no, these are being multiplied. E theta multiplied by this. E theta, blah, 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 blah. No, well, they're being multiplied, but all these are being summed because summation. 1 plus this plus this. Let's just continue reading. Now the gradient of a scalar field, is also irrotational. Irrotational and solenoidal. Love. I think this is basic stuff, but let me make sure. Irrotational. Before I mix them up, which could be a really big issue. Irrotational and solenoidal condition. It's said to be solenoidal if the divergence is 0. Okay, let me write that down. Solenoidal. Divergence is 0. Irrotational curl is 0. Okay. The gradient of a scalar field is always irrotational. Gradient of scalar field is irrotational, which means, so we're pretending this guy is this guy here. So that means gradient cross gradient this guy equals 0. Yeah, gradient of a scalar field is irrotational. Yeah. Hence, this cross this equals 0. So we're treating this as, they're saying that this guy here is actually gradient phi. But the gradient of a scalar field is irritated, hence. Are we actually talking about a scalar field, or are we talking about this coordinate still? I think we're still talking about this coordinate. Yeah, because we're using this now. So yeah, gradients, this is this. Yeah, makes sense so far. Since, let me eraser. You are in the way, faster me. Okay. Is there anyone in chat? Nobody's in chat. Hallelujah. How long have we been going? Almost an hour. Okay. Since this equal this, which we made some kind of sense with from here, we find that a generalized coordinate curve has a natural curliness of, okay, so there's a coordinate curve here, and we curl it to find the curliness. That is how I read this. We curl it to find the curliness. This is the curliness. We do that by getting rid of this guy. This. You. This equal this equal this minus this. Minus HJU, blah 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 blah. I think I get it. I think I get it. It's kind of weird, but I think I get it. Do I? Do I cross EJ? It's kind of weird. It's kind of weird. It's really weird because one side of the equation is zero, so you can do all kind of weird stuff. It's kind of weird. So this cross this equal. We do the product rule thing. Well, first let's send across the HJ, right? No, we do the product rule shenanigans to get this. Now we send across. Wait, this. So we want to get this alone. We have this guy here. Do we have any other guys? We have this guy, but he's kind of connected to this guy. Let's just use this guy, it's cleaner. So we know this is equal to zero. So we can just be like, oh, you're zero. Goodbye. And since we want to get this alone, we carry this across. And then that's how it gets negative here. And we divide by, wait. Yeah, it makes sense. We divide by this guy. So right now it's minus 1. But when we divide by it, it'll become 1 on the other side. Because minus minus 1. It'll be on top of the numerator. Which is why this guy does not have a minus 1. Yap. This equals this. This is the curliness. The curliness of a coordinate curve is, oh my god, negative the scale factor of that curve, coordinate curve, multiply by the curl of the coordinate curve, the curl of the coordinate slash coordinate curve, I don't know the correct word, and the gradient of the reciprocal of, is that HJ? Gradient of the reciprocal of the scale factor of the coordinate curve. Very insane sentence. One consequence of this is that the curl of a vector field is this, yeah. The curl of a vector field VR, which is this, has contributions from both EJ and VJ. Curl. So yeah, if you curl this guy, boom, this guy contributes, but also this guy contributes. Both contributions can be combined into a simple expression with the help of stuff. 1.5. Is this in the future? No. This is from the past. Okay. Curl of V equal the summation Yeah, they just turned this into like what? VI? VI? What's I doing here? Um, this cross EJ, HJ, HJ. Why are these HJs here? Why is this VI? What? It should be VJ. This EJ, VJ is VJ. I think it's a typo because down here there's only VJs. It has to be a typo. Uh, Copium, it's a typo. It's a typo, it's a typo, it's a typo. Okay, and then this guy comes down. What are we doing next? It looks like some kind of product rule or chain rule or whatever. Um, so let's examine how they actually do this. If you have a curl of like a product thing, do no, no. I was going to ask if we took that out because it's constants, but I see we're doing the gradient of them here. Um, hmm. We take the gradient of one thing. It's kind of weird. This is weird. This is weird. I'll have to I'll have to look that up later. How do you do curls of products and stuff? Because why are we bringing this guy with us? And why not everyone? Hmm. Okay, let me send back my confusion down to green yellow. So we we're taking this guy and we're just shoving these guy down. And now it's these guys' turn to get put in front of this guy. And it's strange, it's weird. Now we have gradient HJVJ cross EJHJ, which is just this. HJVJ is this is this, right? Nothing fishy. Nothing fishy. So this is zero. Is this zero? Is that what they're trying to say? Let's throw out the thing. I, J, K. Del X. Del Y, del LC. EJ. What does EJ mean? 100 is that how that works? What is EJ? EJ. EJ. I'm trying to think if and is it del X? Maybe it's like del U1, del U2, del U3. Hmm. EJ. I think I think two of these will be zeros and one of them will be one. Either that or some weird shenanigans where each of them have a relationship with EJ or something. Uh, if this is the case, we have this will be zero. This will be del one, del Y, and this guy's always with him. Well, maybe we can bring that outside. Maybe. Um, del one. Why am I writing one? Next we have boom. That's for I. I in quotation marks. Um, maybe we can call it EI, E1. I think we call it E1. Uh, Next we have del U1, del U2, del U1. No, minus del U1 because we're dealing with this guy now. E E2. Okay, and all of this is being multiplied by 1 over Hj. Very weird stuff. Del U del U1, yeah. Del U2. Wait, I think so. We want this to be 0, so these two will be equal. And what I'm seeing here is we're taking the partial derivative of 1, which will just be 0. Yeah, so yeah, maybe, yeah, maybe, 0, 0. We move on. We're left with this. What are we even trying to do? We're just trying to simplify. What contribution can we combine into a simple expression? Yeah, we're just doing it with civitas. Um, del, okay, cross. So none of these are like J8 components, so we're gonna have to bring in another guy of our own. So Liver Civita, we can do any symbols we want really. Um, this guy's using I, J, K, Y, J. We can actually use a J. Epsilon I, J, K. 1 by H, J, del S. Why are we changing this to... Hmm, hmm. I don't like this. I don't like this. I'll do it my way and then I'll do it the two ways to see what's going on here. So del X, HJ, VJ, right? We have this. Del X. And let's call the subscript L. And then we have EJ. Wait, this guy already has a direction. Is that normal? I think that's normal. Yeah, that's normal. So then we have E. Is that normal? The jth component of something means no. This guy is the jth component. Ah ah. Hmm. Here E J H J M epsilon L M N. Hmm. M J component epsilon K M H J. It makes sense. It makes sense. Sadly, and the I comes from. It makes sense. Okay, it makes sense. All right, this thing is actually um like something like HJ, um eject component or something. I'm used to seeing it like this, but I'm used to doing it in level servitors in two ways. Either you have like a component in there, and when you have a component, you can like break it down, or you have no components, and then you bring in your own guy, like EK. Um, let's go. Hmm. Hmm. Epsilon JM Epsilon IJK. Different color, different color. Not you. You. Let's see if our substitution works here. Del equal EI of R, uh, del SI, del SI, 1 over HJ, well, just do HJ, VJ, 1 over HJ from here, this guy here, 1 over HJ, 1 over HJ, 1 over HJ, VJ, del SI, VJ, EJ, bling, bling, IJ, EK. I'll look at this closer uh, later. We move. The result shows that besides the usual Cartesian contribution proportional, show that beside the usual Cartesian contribution proportional to del Vj del Si, there's an additional effect proportional to, oh my god, proportional to this that arises from the curliness of a coordinate curve. Okay. Uh, IJK, VJ, VJ and HJ, del HJ, del SI, del HJ, del SI, HJ and VJ. Besides the usual Cartesian contribution proportional to del VJ, del SI, this guy here, this thing, there's an additional effect proportional to VJ on HJ, VJ on HJ, del HJ, del SI, that arises from the curliness of a coordinate curve. Okay, okay. Another useful way of writing this slop is curl equal. Yeah, this is probably what I was trying to think of. Is curl of v equal summation ijk epsilon ijk del ui hj vj ek. Yeah, this is closer to what I had in mind. When you sum it up, well, when you convert it back to like cross product and determinant, you get this h1 e1 h2 e2 h3 e3 del w1 del w2 del w3 is basically this dot this, but one of these guys goes up here One of these guys goes down there. Oh, why not the other way around? H here. Hmm. I think I get why, but I think I get why. To derive a similarly compact and useful expression. Yeah, this is kind of pleasing to the eye. This bling 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 del LE1 H1 V1 H1 H1 H1. Oh, you can't take that out because you need H1s throughout in order to row reduce. So you can't do that. Um, what time? Oh, 1:15. To derive a similarly compact and useful expression for the divergence of V, we start with the curl of U. Oh my god. We start with the curl of this. The curl of this equal the curl of this equals gradient cross gradient UN. Okay, let me try to make a notation for this. Gradient of this plus this. Okay. Gradient of this plus this plus this. Oh, jagged line, um, hook, hook from below. I'm trying to make like a little symbol to be like this means plus. Maybe like, yeah, I think that could work. Like a mu or something. So this goes into this, and then you add this. Well, cross that. Uh, and then this goes into this. Cross this, maybe? Maybe? You. That doesn't look like the case. This goes into this, and cross this. Plus, plus, I guess the idea is over here, the gradient has already been used up, but now it's not used up yet. He's still going to be used on this guy. So I guess that's how you can think about it. Like even though you still see a gradient here, it's already used up before it's being curled. That's how I'm gonna think about it. Um, Now we have, oh my god, these two curls equal one curl somehow. EM over HM plus EN over HM. Okay, using 1.134. Let's see what that's about. I have written about I've written up on this so much. Uh, so one of these, never mind. What a 1.134. 1.134 is this. The gradient of U equal AJ, HJ, EJ, equal the gradient of this. The gradient of a coordinate, equivalent near coordinate, any coordinate, I assume. Are those constructed from curvilinear coordinates? Well, let's just say curvilinear for now. The gradient of a curvilinear, equivalent near coordinate, any coordinate, I assume. Are those constructed from curvilinear coordinates? Well, let's just say curvilinear for now. The gradient of a curvilinear, equivalent near coordinate, any coordinate, I assume. Are those constructed from curvilinear for now. equals EJ on HA, like in the direction of said coordinate. Gradient of a coordinate equal E in the direction of the coordinate over A divided over the scale factor of the coordinate. But but where did this guy go? This guy is zero. Why is this guy zero? Because okay, I see why this guy is zero. This is, let me write this for future me if I ever look back at this. Zero because curl of gradient of something uh, is irrotational. Is irrotational. Irrotational. Now we have this. Hmm. It's on M and K, EK. Hmm. I thought I was past this, but I guess there's some confusion here still. A cross B, right, equals AJ BK C. Oh yeah, I forgot I. Okay. AI BJ CK well EK epsilon IJK. Boom. This cross this AJ. Hmm. Hmm. I guess what's tripping me up is this already has a direction associated with it. But what if this secretly was already AM? If this was secretly AJ or AM, would that change anything? AJ cross B. I don't think it would, because we still need to go through all these permutations. So all that means is he's already at one of those permutations, I guess, maybe. And and maybe these two are allowed to be together. Like we're allowed to use M and N, like both of them at the same time, because for some reason we know both of those are orthogonal. To derive, we can start with this. To derive a similar compact and useful expression for this, we start with the curl of, why we started with the curl of this? Like, what even is this? Why is that important? I'm sure all will be made clear. That's my catchphrase, all will be made clear. Um, so yeah, I understand. I understand what's going on now. Uh, MNK, yeah, yeah. The curl of whatever this is this. UM, UN. Since this vanishes for M equal N, yeah, that's just how limitativas are. If two are equal, it's zero or something. Right? Right? Yeah. Yeah. That's how limitativas work. Since this vanishes for M equal N, for which the permutation symbol is repeated, yeah. The non-zero cases m not equal to n. For example, this. For example, this case where this is the result. Why is this not summed up against m and k? K. I guess it's not necessary. Maybe. Maybe. Or has that always been the case? Or maybe you only need the summation ij's if these guys are not already split up. I feel like I need to zoom in on this some more at some point. Because I think I remember there being ijk down there normally. Um, for example, this equal this, and then they just have the negative, like we switch around stuff. U2, U1. Yeah, if you switch these around, you get negative, even though you're not actually switching around across the cross, but you are switching m for n, which for one, like, that's like one switch. Every one switch, you turn the expression negative. That's how Levi-Civitas work. Now, according to all the way up there, I'm not going up there. The curl of any vector field, is always solenoidal. Is that true? The curl of any vector field is always solenoidal and free of divergence. This holds for all. The curl of any vector field is also solenoidal and free of divergence. This holds also for the curl of the last equation. That is, you're saying curl, but I'm saying dots here. Well, solenoidal means divergence, I guess. So, yeah, I guess. This holds for the curl of the last equation. The curl of any vector field is also, let me write that down. Like over here, I mean. Curl, let me write it down over here. Curl of a vector field is solenoidal, which means if you put, if you find the divergence of it is zero. So the point they're trying to make here is that this thing here is this cross a vector field. And I think from earlier we saw that EI and PI is H123 on HI. So all the guys divided by EI. Kind of weird. Oh, it's just this. It's just this. Hmm. Hmm. So this is this. U1, U2. This holds also for the curl of the last equation. Yeah. Since the divergence of this, oh my god, oh my god. But actually this is important, so let me go and somewhat highlight these guys because This is important in like understanding how uh um 4 boom. No, I want to draw 4 past status. Boom. This seems important. Anything else? This seems important. The understanding of the curl and divergence of like a product is. This guy seems important here. I think that's it. I think that's it, yeah. Okay. Back to normal size, please. Thank you, thank you. Your work has been, you have done some very good work, my friend. Nobody's there. It is just me. Uh, since this equal this, okay, divergence of whatever this is. Let's bring this to the top. Dot. Hurry up, reach the top. -1 equal the gradient of one guy. I think I'm getting the hang of this. The gradient of one guy. So gradient of pi -1. Then that will be dot producted with ei. And then now you add this to well, what do we do this? We do pi -1 divergence dot ei. I think that's it. Yeah, yeah, yeah. This means that again, this dot ei dot pi. The curl of any vector field is always solenoidal. Curl of is always solenoidal. Solenoidal. Bling. Is this a vector field in disguise? This guy here? Are you? Are you? EI on. I feel like you might be. I feel like you're holding secrets. Uh, let me see what the next line is. The next line. Oh wait, no. This is the 0. This is the 0. So we bring this guy. This is 0. Bring this guy across. We divide by this guy to get pi. Since we carried it across, is minus. Minus pi bling, yeah, equal this. What? This equals this. Yeah, I've made peace with this, yeah. Equal minus pi. Okay, well, they're just simplifying this, I guess. Let me change color. There's too much pink in it. No offense to pink, I guess. Uh, so del. Oh my god. Minus pi. Okay, You converted it back to 1 over pi, yeah. And this guy is actually del. That guy is del si. Del si. 1 over pi. We have this guy. Dot ei. Dot ei. Okay. The magnitude of this is 1. The magnitude of this is del si. So we have this. Thumbs up. I agree. I agree. Yippee. This means that since this equal this means that the divergence of coordinate does not in general vanish. In other words, the curliness of the coordinate curve contributes to the divergence. The curliness of the coordinate curve, so apparently this thing here is the coordinate curve, contributes to the divergence. We are now in a position to put these results together to determine the divergence of a vector field written in generalized. So all of this was just some big grandiose plan to bring them together. Okay. Oh, we're almost. We'll see if we finish this. We're now in a position to put these results, determine divergence of a vector field written in generalized coordinates. Divergence of a vector field. Did we do the curl of? Yeah, we did do the curl of this guy. Okay. So divergence of V equal. Okay. Summation I, we just broke this up into like there's normal stuff. Summation I, we're still working on this. We introduced PI. What's PI? I think PI is just a bunch of H shenanigans. We didn't need to. Let me look at the previous case. Over here we brought on HJ for no reason. What did I do? What did I really do for us? It made our lives more complicated, yeah. That's for sure. HJ. What if we didn't bring in HJ here? If we didn't bring in HJ, I guess there'll be nothing to look at, I guess. So we're just bringing in stuff to look at it. Summation I long, summation R, okay, we're actually doing stuff now. Okay, this guy, no, change color, please. Oh, I'm colorblind. Well, not actually colorblind, but I didn't see it was a different color. Let's go with this first. Divergence. Well, gradient. No. Gradient? I guess gradient. Gradient of P I V I dot E I over Pi. Why are we grouping it like this? I don't know. That's what we did last time. I'll figure out eventually. Plus, now gonna we're gonna bring this guy in front. So Pi Vi gradient dot EI and PI, right? Is that the case? Okay, gradient dot EI PI PI. The only difference is I put it in front. Is that an issue? I don't think it should be an issue because this is a number at the end of the day, right? And it's not like this guy's gonna magically creep his way over here. Plus gradient PIVI dot, yeah, correct. What we can do now, what can we do now? I think one of these guys disappears because this is actually this in disguise or something. And the divergence, wait, no, this isn't the divergence anymore. So maybe I'm talking about this guy, yeah. This guy is secretly a curl of V, divergence of a curl of a vector field, 0. So this whole thing will be 0, so this guy goes over here, right? Yeah, maybe. EI on PI. EI on PI, yes, is a curl of a vector field. It's a vector field because even if it wasn't before, it is now because the gradient function. Um, blah blah blah. Yeah, blah, 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 blah. So now we have this. Um, PIVI. We still need to differentiate it. Yeah, EI. EI. We can change the gradient. We saw over here that you can basically like operator identities. You replace the gradient with EI del SI. And it works out well because the dot product of EI and EI should just give both EI should disappear because of the dot product. So you'll end up with del SI of PIVI and 1 over PI from there. Yeah. We'd also reduce the curl of V and the divergence of V in the OCC system to something involving derivatives of scalar fields. We reduce the curl and divergence of V in an OCC system to something involving the derivatives of scalar fields that are similar in structure to those in rectangular coordinates. Rectangular coordinates. Okay, yeah, I agree. Yeah. All one has to do is put in an appropriate scale function before a differentiation and to put in an appropriate scale function. Yeah. Before differentiation and to divide it out afterwards as shown in 1.13. Yeah. Basically derivations. It is also not accidental that the formula for the cross comes from gradient of a coordinate, while that for the divergence, it is related to the gradient of a coordinate, the product of two coordinates, the product of a coordinate and the gradient of a coordinate. The reason is that the surface integral of the curl of V, surface integral of curl of V, surface integral of curl of V is related to a line integral circulation of V according to Stokes' theorem. Hence, it depends on the linear changes. The reason is that the surface integral, blah blah blah, is related to a line integral according to Stokes' theorem. Hence, it depends on the linear changes of the coordinate system. Linear changes of the gradient of Ui. For divergence, surface integral of this. So this is for the curl, which is the easy one, right? For divergence, Gauss's theorem relates a volume integral to a surface integral, in which a scale factor appears quadratically. I suppose, since we're dealing with areas. Yeah, maybe. The derivation of bling and bling directly from these integral theorems will be left as x. Oh my god. Okay, I'm fine with that. I'm fine with that. Is there anyone there? No one is there. Hallelujah. Oh my god. I love this so much. Okay, calculate. Oh my god. Hmm. 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 How long am I serving? Almost 2 hours. How much pages have I went through? I went through like half. 1, 2, around 4, which is the average. I counted it. When is a good starting point for next day? Unit operations. I think that was a good ending point. That was a good ending point. Ah, goodbye, end of stream. Thank you so much, everyone, for being here. Thank you, Dashi. Thank you, Dashi, too. Thank you, differential operators. Thank you, scale factor. Thank you, circular spherical coordinates. Thank you to my gradient over there. Thank you to my curl. Thank you to my DUIs, my HIs, my UJs, my UJs. Oh, you UJs. Let me end stream. Goodbye. The end.